Hi, in this video, I'm going to talk about static equilibrium. So whenever you hear equilibrium, the definition of equilibrium is net force equals to, that's right, the net force equals to zero. And equilibrium can be static or dynamic. Static equilibrium is the case that an object is at rest. It's not moving, and the net force on the object is zero. We say such a case as static equilibrium. And in this video, we're going to talk about different types using the condition of a static equilibrium. We can find out about the tension forces and stuff like that. So let's get into the example problem. Here. So any equilibrium means net force is zero. And static equilibrium still, this is true, net force is zero, and it's at rest. So let's see this example. That's also in a book. That let's see here. This is the ceiling. Okay, and Nellie Nelson, she's hung by the two ropes. Okay. Let me see. She's hung by two ropes. Like this. Something like that. So she's supporting herself from these two ropes. She weighs, let's say, 600 newtons. Yeah. So she weighs 600 newtons. So over here is better. Over here is 600 newton. What would be the tension force? What would be a tension force? Can you draw the tension vector? So imagine that in between this rope, there is a scale. So let's see this. Not the whole thing. I didn't need the whole thing to disappear. In here, there's a scale to measure. So here is another scale to measure. So in between this rope, there is this kind of a scale to measure. Can you draw the tension force? Tension vectors. For each of ropes. How to find that? So what we know here, how to find the tension vectors after I draw this. So first of all, I approximate 600 Newton. I say this blue arrow here is 600 Newton. So this length is the 600 Newton downward. What else we know about this? When you hear you have to draw tension vectors, what else we know? Tension force, what's the direction of tension force? The direction of tension force is always along the rope. How many tension forces we have? I guess we have two tension force. But if they both have these ropes the same angle, then they're gonna have the same tension force, same magnitude, just pointing in a different direction because the rope is pointing in a different direction. So now we want to approximate so we know the direction of tension vectors, right, along the rope, but we want to approximate the magnitude. How do we do that? What else do we know? What's the motion of this Nellie Nelson? Is she moving? If she's moving, what kind of a motion? She's at rest, right? So she's at rest. When she's at rest, what is her net force? Her net force is equals to 0. So all the forces acted on here, adding up all the forces on her hand is not moving. So if you add up all the forces acting on her hand, it should be equals to 0. So we know that this 600 Newton here, okay, so this is just to take out that here, this 600 Newton, this is the 600 Newton, her gravitational force, plus 2 tension forces. The rope is, let's say, the rope is pointing in, let's say, like this kind of a direction. And another rope is also pointing in a similar angle, right? Like that. So we know that tension force has to be along in this dashed green line, but we gotta approximate the magnitude to make her, to make sure that net force to be 0. How do we do that? Let's see. What we know is that tension force is gonna be somewhere here, right? And then adding this tension T1 and T2 here, right? T1 and a T2. So we know that a net force on her hand is equals to Fg, gravitational force, plus T1 plus T2. This all should be equals to 0. And 600 Newton downward. And the T1 plus T2 has to support that 600 Newton vertically downward. That means, let's flip this blue 600 Newton, okay, into the opposite direction. So like this. This is the opposite of a 600 Newton, vertically downward. So now we can say that this T1 and this T2, T1 plus T2 is equals to minus gravitational force. You see, the T1 plus T2 has to be equals to minus Fg. So this 600 Newton minus 600 Newton here, this line is going to be the resultant of T1 plus T2. Then we can do the parallelogram backward. What I'm going to do now is to draw the parallel line to the T2. So here we have a T2 that's pointing in this way. So I'm going to put the end of the parallel line right to here, and then just see where it crosses on the rope. Same thing, I'm going to do it so you see that this line is parallel, this line, and this line is parallel. And I make sure that they intersect at the end of the minus 600 Newton. Okay, so then we can write, now we can say that T1 is this much, and then T2 is this much. T1 why it doesn't come up? T2 T1 and a T2. I hope you see it. So that's how you can approximate the amount of tension force when you know that there's going to be 600 Newton downward. By the way, what happened to the, so we just did the case that this is my daughter's necklace, and then using a ropes for my son's toy. But if you have the rope that's hanging the same angle, you can see the tension force is going to be the same. What if like this? Do you think the tension force in each rope is going to be the same? What would be the best way to hang? Efficient way. So let's say this rope is very fragile. Would you like to hang this necklace? If this necklace is, let's say, very, very heavy, would you like to hang it like this, or would you like to hang it like this? Which way is better to support heavy necklace? This or this? Vertical, two verticals or two horizontals? Which one makes sense? Using a parallelogram. So no matter what, let's say this necklace weighs 100 Newton downward, right? What would be the tension in both each string here when the necklace is 100 Newton? When it's completely vertical, like this, two vertical rope. What happens if I change the angle? Wider and wider and wider. What happens to the tension force? Increases, decreases, or stay the same? And what happens when it's completely horizontal? So that's the end of the static equilibrium. You might want to think about the questions that I just asked, and then I'll see you in the class.